Hello, students. I want to give you some guidance on the problem set for Chapter 9, Assignment 1, and Halliday-Resnick. I'm just going to give you some guidance. I'm not doing the entire problem, but hopefully this will be of assistance. And also, I'm hoping to show you, if you need it, a little bit of how you can use the textbook to assist you in answering these problems. So the first problem is number 2. And notice, this is section 9.1, center of mass. And this problem is just asking us to calculate the center of mass for 3-point particles like this, 3-point masses. We're trying to find the x and y coordinates. And then there's a follow-up question. So we can go, if you don't remember how to calculate this, right? You go to this portion of the text right here, all right? And this is telling us how to calculate the center of mass. So if we want to find the center of mass, the x center of mass, right? We use this formula. We do the product of all the m1 and x value, m and x values divided by the total mass. And then for the y, we do the y values and the masses divided by the total mass. And that gives us the center of mass. I think there is an example problem here. The same sort of idea here. So you can sort of see a similar type of problem here. So hopefully that one is pretty straightforward. Moving on to problem number 4. In this one, instead of given point masses, we're given 3 rods like this. But they tell us that each they give us the mass of each of these rods, and they tell us that they're uniform. Okay, so they're constant density rods, which means the center of mass of each of these rods, each rod has a center of mass that is, the center of mass of each of these rods is at the actual center of each of these rods. So you could treat this just like the previous problem of 3-point masses, just like we did this problem here, right? With these 3-point masses. Don't just ignore the dots that I drew, but this was just 3-point masses. We can treat this as 3-point masses, just like that are at these positions, and the vertical ones have this mass, and the horizontal one has this mass. And we could find the center of mass of the system in the same way. We don't need to go through a complicated integral to do these calculations, right? We just need to say that, okay, the center of mass of each of these is at these coordinates. Okay, so it's a little confusing. They changed the Zoom layout here. All right, so moving on to problem 6. Problem 6 is the same idea, but it's in 3 dimensions instead of 2 dimensions. So if we could, it's a little maybe confusing to see with the in 3 dimensions. So I'm just going to try to draw, I'm going to try to replicate the sort of coordinate system real quick here, sort of like this, right? And you see there's a plane that's sort of right here. And a plane that's like right here. And a plane that's like here. I'm not perfectly replicating it, but I hope you get the idea, right? These are the, this is the lower plane right here. And this is the left side plane right here. And this is the back plane right here. Well, each of these is also a uniform plate. So the center of mass of each of these planes is at the center of each of those plates. So like right there, uh, like right there for that one. And then this one is right here. And then I don't know why. Got something funny happening here. I guess it's the wrong here. There we go. So those are the center of masses, and it says that each side is L over 2. So note that this is X, and this is Y, and this is Z. So this point right here, right, if we were to ask what is that coordinate, X, Y, sorry, X, Y, Z, it would be an ordered triple, right? The X coordinate would be L over 2, and the Y coordinate would be 0, right? We didn't move anywhere. We're along, we haven't gone anywhere along that Y axis. So that would be 0. And then the Z coordinate would also be L over 2. And this coordinate would have coordinates, right? The X coordinate, this X coordinate would be 0. This would be 0. And the Y would be L over 2. And the Z would also be L over 2. And then this one's X, Y, Z coordinates, the X piece would be L over 2. And the Y piece would also be L over 2. And the Z piece would be 0, right? Because this plane is on the bottom right here. So hopefully you can follow along that logic with the other three planes, right? The front plane, there's a plane here in front, and then there's a plane on the right side. That's this plane right here. Hopefully you can go on and figure out what those coordinates are, those center of mass coordinates are, and then you can do a center of mass calculation in 3 dimensions, just like we did in 2 dimensions. But that's maybe the confusing part to understand with this. Okay, so moving on to number 12. How do I, uh, that's not what I wanted to do. How do I clear everything? There we go. Clear all drawings. Okay, so now we need to go on to number 12. So number 12, we are given this initial velocity, right? This is the 20 meters a second, and this is the 60 degrees. Okay, and it says up here there's some explosion, and this explosion causes this piece to fall straight down. It's going to land right here. And so then it asks us, well, where does this other piece land? It's going to land somewhere, way down here, right? And it asks us, how far does this other fragment land? Okay, well, if it never exploded, okay, it would have continued to follow this parabolic trajectory, and it would have landed over here, right? This would have been the landing piece if no explosion had occurred. Okay, and it says it explodes here at the peak, I think, at the top. Yeah, so there, we're at the top. It explodes at the peak here. So if you remember this equation, R equals V naught squared over G sine 2 theta. Okay, that would tell us what this value should have been. That's where the piece should have landed if there had been no explosion. So this value right here, that value is half of R. Okay, so it lands at half what that distance is. So you should be able to figure out what this R is and then figure out what half that is. And that's where this piece lands. And then you can use the fact that the center of mass should not change, right? You can say X center of mass equals X1, M1 plus X2, M2 over M1 plus M2. And it says that they're equal mass, so these are each half the total mass. So all we got to do is we could just call each of these instead. We could just say this is x1 m over 2 plus x2 m over 2 over m total mass, right? Because m1 over m over 2 plus m over 2 is just m. So, and that is going to, together, these two things should equal R, right? Whatever R is. So we know that this x1, right? We know that that is R over 2, right? X1 is R over 2. So then all we've got to do is figure out what this X2 value is. And hopefully you see these M's will, of course, cancel. So if you know this R, and then you know that this value here is R over 2, you should be able to figure out what this value here is. Okay, so that was number oh, that was number 13. Whoops, that was number 13. I skipped ahead. I missed number 12. Okay. And this is sort of like the question we did on the check, right? They're holding a pole and they pull themselves until they meet. How far does the 40-kilogram skater move? So what you have to do is figure out what the center of mass is, right? The center of mass is not going to be halfway. The center of mass is going to be closer to this skater, okay? And then you've got to figure out that you got to realize that they're both going to end up at the center of mass, right? That the point is that they're going to end up at the center of, they're going to meet at the center of mass. So if you know where they meet, you should be able to figure out how far this one moves. And the smaller mass one is going to move the greater distance. Okay, moving on to number 15. So you should be able to figure out the acceleration of this system. We've done this type of calculation many times. Now, what we're asked then is to find the unit vector notation of the acceleration of the center of mass. So up until now, we haven't had to find the velocity or acceleration of the center of mass. We've just been looking at the positions. Well, go back in the chapter. All right, let's go here. Key ideas. Well, if this is your center of mass equation, right? Then you can think of the velocity of the center of mass as the derivative, right? We could divide this m over here, right? We could always divide both sides by m like that. And then what we have here is that's the center of mass, like this. Well, if we wanted to take the derivative of this, well, the derivative of this would be the velocity of the center of mass. And you would have this equation here, which is like the center of mass equation, but instead of with positions, with velocities. And then you could do it again with accelerations. So let's go back to our problems. And that was problem number 15. So these have the same magnitude of acceleration. The difference is this one's accelerating to the right, this one's accelerating down. This one has only x acceleration, this one has only y acceleration. The y acceleration of this piece is 0. The x acceleration of this piece is 0. So you only have to find the acceleration of each individual mass. You just have to make sure that then you multiply it by the right mass, right? M1 for this one, M2 for this one. And then you can find the acceleration of your center of mass. Then you want to find the velocity as a function of time. Well, if you know the acceleration is dv dt, so v equals a dt integral. But if you remember, the acceleration of this system is constant. So v equals a t. All right. So the velocity as a function of time can just be found, right, by multiplying each piece by t. Right, now that we know, since you know the acceleration, you can find the velocity. And then hopefully you realize these are both linear. They're both going to be linear. So this is going to be some sort of a diagonal, right? One piece is going to be moving, this piece has some horizontal velocity. This piece has some vertical velocity, but they're both constant. All right. So the center of mass is going to be moving sort of downwards, down and to the right, like that. So it is not curved, but it is in a straight line. You should be able to find the angle, right? And if v is some vx I hat plus vy j hat, actually it's really a minus. Technically, this is going to be a minus value because this one's going down. Then theta equals the inverse tangent of vy over vx. So moving on to number 17. This one is similar to the problem from AP Classroom. You just have to realize that the center of mass doesn't change. There is a confusing little bit with the fact that we don't know what the center of mass of the boat is, but maybe call it 0 and see if that helps you. That might be a little trick to figuring it out. The other thing to realize is what we need to just figure out is how much something changes. We don't need to know the actual position. Well, we do need to know how far the dog is from shore, but we know the dog starts out 6.1 meters from shore. But I guess a good way to sort of do this is you figure out what the initial center of mass is, right? X center of mass initially is going to be X, here, 4.5 kilograms times 6.1 meters plus 18 kilograms times the initial position of the boat, XB initial. Now, we don't know what this is, but maybe we want to call that position 0 and make it easy for ourselves. You don't have to, but that might be a way to do this. And then you have the final center of mass. Well, that's not going to change, but the position of the dog and the boat will change. So that's going to be 4.5 kilograms times, it went 6.1 meters, but then it moved to the left 2.4 meters. And then the boat also moved, right? The boat moved to the right some. So there was going to be whatever the change in the position of the boat is. So plus XB, like that. And then you would have the position of the boat, this value from the boat, 18 kilograms times X, the new position of the boat, minus the old position of the boat. Actually, maybe you don't need this. You might not need this term here. But if you made it 0, it wouldn't matter what it is. So but I think maybe you don't need it in either case. I'm not entirely positive. I might need to think about that. But I think if you do this and you treat the initial center of mass of the boat as 0, I think this will work. Although I'm not positive. So we might look at this one in class for a few minutes. Then number 19. So we have a truck and it's traveling north. We've got a truck, it's traveling north, and then it turns east like that. What is the change in the truck's kinetic energy? So notice we're going to have to convert these values to meters per second, probably, or do some sort of, conversion along the way. So the change in the kinetic energy is just, right, delta K, that's just 1/2 m v squared minus v initial squared. Okay, but what is the change in its momentum? Well, to figure out the change in the momentum, we would have to realize that this is a vector, right? So the initial, you would have to realize that you went that this is your, if this is P initial and this is P final, that this here would be delta P. Or actually, let's see, this is P naught plus P final. So we want to do P minus P naught. So that would be like that. So I'm sorry. So this would actually be delta. That would be your delta P. That'd be P minus P naught, right? That's minus P naught right there. So that vector would be your, this magnitude here, that would be the change in momentum, okay? So you'd have to realize that you lose all of whatever this momentum, because you're no longer moving north, and you gain everything that's moving east. So you have to, you can't just, it's not a scalar. That's the important thing to realize. It's not a scalar, right? It's this piece right here that you've got to calculate. Number 20 is, they give you the initial momentum, okay? And they tell us that this is the initial momentum, this is the final momentum. And what was what initial angle was the ball launched? Well, if you remember, V, like Vx, right, is V naught cosine theta, right? So, so cosine theta equals Vx over V naught. Well, that is also going to hold true for Px over P naught, right? If we multiply both of these by M, wouldn't be any different, right? Just the M's would cancel. So, but we could just as well say this is Px over P initial. Now, the thing is, this is Px at launch. This is Px when you launched it. However, what you got to realize is this, what happened is basically just this. A ball was struck at level ground. Like you struck it like this and it went like that. All right. And this is P and that is Px. But up here at this point, you got to remember that value, this value is the same as this value, right? So we know, if we know this value right here, that is this value right there. Okay, so you should be able to figure out what the angle is by doing that. And then finally, number 21. You have to find the change in momentum. So what there is, it seems like, is a softball has 15 meters a second at an angle 35 degrees below the horizontal. So ball's coming like this. All right. And so this is V naught. And then V final is going to be either V final ends up being what? It either straight downwards or straight backwards. So there's two, either have to figure out it with that situation or with that situation. And then you got to realize that you want to do, again, P minus P initial, right? So these are your final momentum. Your initial momentum, you want to subtract it. So you're looking at two different calculations. So for part A, the idea is, right, so negative, that would be negative V naught. So negative V naught is like this. And then V final is like that. So that would be delta V. So that's for like part A. And then for part B, that's minus V initial, and then V final was like, was straight out like that. So that would be your resultant. I may not have actually, hang on, I may not have drawn this first one correct. So if we send it in part A, that is negative V naught, and V, there we go. That is, we need to do them tip to tail, right? That's V final. So V initial, so V delta V is like that, okay? Or delta P. So that is part A. And then part B, you have this, and you have, right, that's negative V naught. And then you have the final, which would be, no, nope, like, yeah, like this. There, V, and so that would be delta V. So you got to do some vector resolution. Okay, I hope that this was somewhat helpful. Maybe I'll do more of these if it helps people.